Okay, this lab is a lab where we're going to actually look at collisions. We just finished talking about collisions. There were two fundamental types of collisions. What were the two fundamental types? Inelastic and elastic. Inelastic, for our purposes, inelastic is going to mean that they stick together. Elastic is going to be they bounce off each other. Those are the two extremes. And so we're going to look at collisions and determine what's conserved and what's not conserved among two properties. One of those things is momentum. Momentum is mass times velocity. So we're going to use these here to measure the velocity and then calculate from that and the mass what the momentum is of each of the two carts we're going to use. Then you're going to, so it will be calculated. You're not going to do any calculations yourself. The computer will do it for you. It's going to graph the momentum as a function of time. It's also going to graph kinetic energy as a function of time. Now, last class period, we talked about kinetic energy, that is energy, the ability to do work, because it's moving. So the kinetic energy equation, the equation that we use to calculate kinetic energy is very simply, okay, where is it? Okay, it's not here. I'll just put it right here at the top. Kinetic energy is equal to 1/2 mass times the speed squared. So notice momentum is mass times velocity. It's a vector, it has direction. Kinetic energy, mass times speed squared. You cannot define a direction for speed squared. And so there's no direction with kinetic energy. It's just what we call a scalar, only has the magnitude. It's not the same as momentum because it has the square. In fact, you can write kinetic energy in terms of momentum. Since momentum is mass times the speed, then speed is momentum divided by mass. And so kinetic energy can be written as 1/2 mass times momentum divided by mass squared, which is momentum squared over 2 mass. Once again, you have to remember P stands for momentum. I'm very comfortable with that. I just say momentum and I write P. But I want to make sure that it's clear to you where that comes from. Question, Leslie?
What does 3 dots mean again? Yeah.
Those 3 dots mean therefore. Therefore, yeah. There, now it won't be confusing. So, right, so therefore roughly equivalent.
Okay, for a second.
I'm sorry, I didn't hear you, Gabby.
No,
You got it, okay. So we're going to be looking at the kinetic energy that the carts have as well as the momentum and looking to see how kinetic energy changes or stays the same. Now, we have already learned that momentum is mass times velocity, and Newton's second law in terms of momentum is the net force is equal to the change in momentum over change in time. So if you saw that for change in momentum, you have the change in momentum is the net force multiplied by the change in time. So our system is going to be 2 carts. If those 2 carts interact with each other, the force acting between the 2 carts is going to follow Newton's third law. Force of cart 1 on cart 2 is exactly the same magnitude, but opposite direction of the force of cart 2 on cart 1. And so if we add those 2 forces together, if they're equal in magnitude and opposite directions, if we add them together, what do we get? I hope that was 0. We get 0 because they're opposite directions and the same size. That's like saying if I add 5 to minus 5, what do I get? So those forces between the 2 carts will always add up to 0. So we say the external forces, we're talking about the forces acting on the carts other than the force of one cart on the other, because those are both internal to our system. Now on the tracks, we should have, of course, gravity down, force normal up, And then there's probably going to be some friction, which will be opposite to the direction they're moving. You see that my track here is sitting on the desk. Apparently the desk is not level because it's clearly rolling this way. Now, something cool about these carts, they have magnets inside. So I make this come up here. They never touch, but we had our collision. That's our example of an elastic collision. Check to make sure the wheels spin and keep spinning. If they don't, then you have a lot of friction in the tires and it kind of messes up everything. So I actually told Alex to test them just to make sure, but he may not have remembered because it's not like he set them up right there. So a collision like I just showed, and I'll do it again, where the magnets repel them, that's which type of our collision? Is that elastic or inelastic? That's elastic. Because they did stick together, they bounced off each other. Now when we do these, we don't want them to hit each other. If they actually touch, then it was going too fast and we're not going to count that experiment. We're just going to do it over. So if I go, whoops, yeah, there the Velcro made them stick together. They weren't even supposed to touch. Well, clearly they did touch, the Velcro made them stick together. And if I did it really, really fast, right, you hear it bang, they bounce off each other. That bang means that you lost some, it wasn't a perfect collision. So they need to be slow enough that they don't touch if you're doing elastic collisions. Now we're doing both elastic and inelastic. So I'm going to take this one here that has the little plunger thing on it. Okay, this plunger thing is so you can press a button and it comes out. It's not the best of designs. They come out with a much better design since I bought these, but I bought these 15 years ago. So, you get the technology at the time. To put this plunger back in, putting it the way it normally sits, you just push it in. Well, it's easier to hold upside down. Push it in, and then it has a little latch. You see these little grooves? Those come up for it to latch. So doing it upside down is easiest. Then when you have it pushed all the way, and you just push it up toward the top, and then it's in place. And then this pushes it down, so it's not on the latch, and out she comes. So just so you know if those things are out, how to fix it. Now I'm going to put it so that plunger is toward the other cart, and now there's no magnets on the side of that plunger, so they touch each other. And so this is the way we're going to make collisions where they stick together. What do we call the collisions where they stick together? Inelastic. So that's how we're going to make elastic versus inelastic collisions. Now, to make our lives easier, last class period, you had to measure the mass of your carts, right? This lab period, we're just going to assume that each cart has a mass of 500 grams and that this also has a mass of 500 grams. So we're going to make life easy and not measure the masses and assume that they have the 500 they're supposed to have. What you're going to do is first set up the track and level it. So how do you set up the track? You've got the feet, so you got to put the feet on. Obviously, you don't have the carts on the track when you're putting the feet on. That would be silly. Remember, you never want to unscrew these all the way. If you do, we start losing pieces. So you just need to loosen it up a little bit. Stick the little, I loosened it up too much. These here, yeah. If you loosen it up too much, the nut can turn, but if you don't, they'll go right in. I always go about 1/3 of the way in on both sides just to try to get somewhat even. Now, I am not going to spend the time to get this level. Clearly, you can see it's got side-to-side problems because it's wobbling this way. So I would want to adjust the wheels. So there I fixed the side-to-side, but it clearly has not been leveled this way. Let's see what happens if I put it in the middle. Yeah, definitely going down that way, right? So that would clearly skew my results. If I did my experiment like this, my results would not be very good. Right, so you want to level the track. That's the first thing. Okay, so I didn't level it. That means what I do is going to look wrong, and I'm okay with that because I rely on you guys doing it right, not seeing it done right and then saying, well, I'm just going to write down what he did. These slide on the end. is sometimes it's easy and sometimes it's hard. Make sure that you have them so that this thing here should be at, I think it says 0. Actually, I can't read, but there's a notch. So it's vertical. Make sure the top is switched over to cart, and one goes on each end. And I'll leave this up here so you can come up and look at them. And then this will go here. I put that one in 4 just because I looked at it beforehand and that's how I set it up. If you put them in different places, I think it'll work just fine. But 4 and 1 is how I set it up. So now I have my track put together. Part number 1, assuming I leveled it, would be good to go. Now I need to power everything up. So let's go through the power-ups. Yay. Do you remember what I told you last lab about the order of plugging in the power anytime you use a transformer? Like, say you're going to charge your iPhone. First, you plug in the transformer. So there's nothing connected to it when it gets the power surge. And then you plug this into the back. And then we have to connect our USB. The person who designed these USB, is it mini? I think these are the mini, right? Was clearly not a genius. If you look at the connectors, they're often mangled. My son had a Kindle Fire. In less than a year, it was unusable because they're not very robust connectors. That is one of the good things about the lightning ports on your Apple devices is at least they're more robust. It's sad that they're also more expensive because it's the sole provider. Okay, so I have all that connected together. Press the power, it should power up. Now everything's ready to take data. So now let's look at what you're going to do. Your first thing that you have to write down is you're going to, with just one cart on the track, start the experiment and push the cart at a reasonable speed so that it goes from one end of the track to the other. So, of course, I'm not going to make the measurements and do this because I want you to do it and make your own comments. But I'm going to put the cart on here and go like this. So it makes it to the other end. Yeah, there, you can stop. So that's what we're doing for the first one. With just one cart. You observe the graphs. You should have 2 lines exactly on top of each other on each graph, and the third one at twice the height. If you don't have that situation, then you need to check and make sure that these things are angled properly to see the cart all the way across. So this here is so you can get everything adjusted just right. Now you have some questions to answer. So you look at the lines for cart 1. Okay, you only had one cart, but it was recording cart 1 and cart 2. A reasonable person says, how does that work? How can it record for cart 1 and cart 2 when there's only one cart? Is that a reasonable question? This detector here, by default, whatever it sees, it calls cart 1. This detector here, by default, whatever it sees, it calls cart 2. So in this case, cart 1 and cart 2 were the same thing because each detector saw the same cart. That's why they should be exactly on top of each other. Now, I did have the capstone program, because they're opposite directions, it has to reverse the direction on one of them to make them so they're both positive for the same thing. So that's another thing to know. Are they both positive at the same time? If they're not, well, something really serious has gone wrong because I set it up so they will be. But going on. So look at the lines for one cart. Was momentum conserved as it rolled down the track? So that means, does momentum stay the same? So you're going to look at the graph, and what will the graph look like if momentum is conserved? Remember, conserved means, tell me what conserved means. below my hearing level, I heard an answer. As I heard,
It doesn't change.
Doesn't change. That's right. So obviously, when you push it, doesn't count. And if you had to catch it, when you catch it, doesn't count. So you're going to have a graph that's going to have, something like this at this end and something like this at the other end. But if it doesn't change, if it stays the same height all the way through, that would be conserved. If it's changing, if it's going like, you'd say, well, that was clearly not conserved. So you're going to answer, looking at the line, was momentum conserved? Likewise for kinetic energy, looking at the line, was kinetic energy conserved? And then here you're going to explain, in theory, why should momentum, kinetic energy So by theory, why should momentum or kinetic energy be conserved or not conserved? And then from the graphs, how you determine from the graph if it was actually conserved or not. Now, I'm going to have to show you how to do this in just a moment, but I want to get to the only thing that's a little confusing, I think, in this mechanism. You're going to be working in teams of 2. So just for grins, I'm going to say that Alex and I, I'm Richard actually, that Alex and I are working together as partners. Each one of us is going to choose one. He has class until 20 after. Each of us is going to choose one of the 6 experiments we're going to do for inelastic collisions, for collisions where they stick together, to predict what we think is going to happen. So you go to this page, and here's the 6 different trials we're going to do. And we have to choose different ones. So I'm just going to say, okay, Richard chooses this one. And Alex chooses this one. They have to be different ones. And so I am going to do all of the work on this page based entirely on the one that I chose from here. So I chose unequal mass carts approaching at similar speeds. And so what I have to do is make predictions. The instructions are here. Sketch what you think the 3 lines will look like for both momentum and kinetic energy from the moments before the collision till the moments after the collision. They don't need to be perfect. That is, the numbers don't have to be right at all, just the right shape. So I'm going to come here and I'm going to draw. What do I think the momentum lines are going to look like for my case? Well, I chose the one where they're coming toward each other at roughly the same speed. If they're coming toward each other, one of them is going to have a momentum this way and one that way, right? So it's going to have to be that one is a positive momentum. Okay, let's try to make it. And the other one's a negative momentum initially. And if they're roughly the same speed, they should be at the same level. And then I'm going to predict what I think is going to happen when they collide. So let's say that I decide to say the collision starts right here and ends right here. So I just kind of arbitrarily chose. Believe me, the experiment's not going to last. It's not going to be 4 seconds for the collision. But the time doesn't matter. It's the shape I choose. So then based on what I've already seen from what happens when one cart goes down the track by itself, I'm going to make lines, and my lines aren't going to be correct, okay? Don't use this and say, oh, that's what I'm going to look like if I do the case that he did. And then you say this one goes. Okay, those are most definitely incorrect. But I predict what I think is going to happen on the momentum. And then I'm going to do, again, a prediction here of what I think is going to happen for kinetic energy. Here I'm going to write down the trial I'm predicting. I'm just going to say 5 because it was number 5 on that list, and it's shorter to write 5 than to say two carts of equal mass coming toward each other at approximately the same speed. And my prediction, what do I think will happen when they collide? So this is words describing what I think is going to happen. Then down here, I will circle either will or will not. So momentum will or will not be conserved. Likewise, kinetic energy will or will not be conserved. So I'll circle the answer I think will happen. And then I'll give the reason I make my prediction for both kinetic energy and momentum. So you're doing all of that before you do any actual collision experiments. So you and your partner are making predictions. Are your predictions going to be right? Let's go with maybe. You might understand and you might not. Why do we do the labs? To develop that understanding. So you can see how it works and come back if you were wrong, then to confront, what did I think wrong? So do not, please, do not do the experiment and then come and do this afterward. There's no learning then. That's just copying down. You didn't do the what do I think is going to happen, is that really what happened process. So I want you to do all of this before you do the experiments. Now, after I've written this down, now you're going to do the experiments. And for each experiment, and I'll show you how to do this, you're going to scale your graph so it just shows the before the collision, during the collision, and after the collision. And then you're going to look at the momentum from before the collision to after the collision, the total momentum. Not the momentum of cart 1, not the momentum of cart 2, but the total momentum, and say, was the total momentum conserved or not conserved? So each one of these will either be, you can just use yes or no. And of course, I didn't put the right answers, but you can just put, yes, no, to say whether each of these were conserved. So you're going to have a table here, and these are for inelastic collisions, the ones where they stick together. After you have gone through and answered all of these, you need to print the trial that you predicted for inclusion with your lab report. So that means each group will have 2 that are printed. And when I mean printed, once again, I mean save it to PDF so you can upload them to Moodle. So you'll have 2 that you recorded, one for you and one for your partner. You then say, was your prediction about the trial selected correct? If not, what was different? Why? So here's where you get to look at your prediction graphs, look at the one you printed, and say, do those look the same or different? If they're the same, hooray, you understood before starting. If they're different, well, what was wrong and why were you wrong? Then we have based on what you wrote in the data table, that is based on this column here, was momentum conserved? And then the last question on this, based on this column, was kinetic energy conserved? Now that you've gotten this far, you rinse and repeat doing elastic collisions instead of inelastic collisions. So staying with the same trial. So I did trial 5 before, so I'm going to do trial 5 again. And I'm going to do the same thing of drawing what I predict will happen with now an elastic collision, and my reasons, and circling which one I think it will be and why. You go through and you make this table again, putting in just yes or no to say whether it was conserved. Once again, you print the graph for the trial that is the one you did. It says here, staple the 2 graphs you printed. You're just going to upload those 2 graphs to Moodle. And then you finish out by, once again, reviewing your prediction and then making rules about momentum and kinetic energy conservation. Then finally, the conclusions, write down what you learned in this lab. If it worked well, if it didn't, and so on. Now, I need to demonstrate how this stuff works. So let's go to the Pasco software. Alex, why don't you go ahead and start the computers, get them logged in now. So the Pascal software is going to look something like this. I'm just going to open this up. If you see, well, I'll show you what you see. If you see that yellow warning sign triangle, see the yellow warning sign triangle above the Pascal interface, that means that it doesn't see your interface. There's something wrong. In this case, it was because I unplugged it. If I plug it back in, it disappeared. Now it sees it. Now for the experiment, down here in the record, that starts taking data. There it stops. That's how we take data. That's marvelous. There was nothing on there. Well, there was something at the end. Let me hide that. Delete whatever data there was. And let's just check and see if things are working here. So I'm going to start it. There's nothing on there. Okay, so I should have a lot of stuff. A little concerned because what do I see? I see nothing on my kinetic energy graph. What do I see? Nothing on my kinetic energy graph. Okay, because it was scaled wrong. Scaling is always important. So let's just look at a segment here. Here's something else I didn't show you. See this little tool that has a yellow bar with 3 dots above it? That creates a little box for zooming in or selecting data. So I'm going to set that box for just this part of the data and then click the scale button. It should have scaled into that. Does not look like it did it properly. Well, it's supposed to do it that way. Yeah, he hate me. You guys probably aren't old enough to, I don't want to auto scale from 0. Well, forget the auto scale then. Anybody ever heard of Rod Smart? He was a football player who in the XFL had for his name on the back of his jersey, "He hate me." And it made national news because, of course, "he hate me" doesn't really make sense. Anyway, so I got to scale it manually. Scale the vertical manually. So there I've scaled it so it fits the screen. And likewise, I'd scale this one so it fits the screen. The times between the 2 graphs are tied together. So you only have to scale the time for one of them. So you want to make sure that you scale things so they fit. Move these little boxes, which you may or may not have an easy time selecting, so that they're not interfering with your data. And so now I can look at this, and you have 2 lines that are virtually on top of each other. Whoops, didn't actually mean to touch it. This is 2 lines. You can see it's the purple and green lines. And then this one up here is the sum of the 2, so it's doubled. Likewise, in the lower graph, these here are right on top of each other, and then this is the sum of the 2. So that's the way it's supposed to be, except for you're going to have the single cart go all the way across the track for your test. It's not going to look like this. The reason is I want you to actually have that thought about, was momentum conserved, was kinetic energy conserved from your actual work. Now when I'm ready to take data, I'll just delete this because I don't need it anymore. And Alex, why don't you come up here? We're going to do an experiment that has the masses wrong. Yes, it's not close to low. That has the masses wrong. So that means that our data is going to be incorrect because the masses are wrong. But it'll be a real collision. So, yeah, just make them come toward each other at roughly the same speed. So Alex and I are communicating like this. I say, "You ready?" So I'm going to go ahead and start it. And when I start it, then he's going to start his thing. Okay. Was that a good collision?
I don't know that I can see that standing in front of me.
That's true. But I don't think it was a good collision. I think they hit each other. So we need to slow our roll just a little. So we'll do it again. Okay. Now, where's my data? It's all way over here at the left. So let's auto scale it. Here we have everything that we took. And I have to find where was the collision. Where was our collision, Alex?
Well, hopefully not one of the spiking points.
Oh, wait, I forget. I got to do it down here. I want to do this like I would anything else. So if we look at this, we had Alex started the two going. Here is where they weren't moving. Here, this one's moving one direction. This one's moving the other direction. Whoa.
They weren't moving quite the same speed.
Yeah, they weren't moving quite the same speed. But yeah, this orange or the purple, violet, magenta, that's what it is. That's actually that's cart 2. And the total is the one in between, because one's positive, one's negative. It's what's in between. And then the collision is where things changed. So where did things change? Things were changing between about 1.0 seconds, about here. Well, here's where they started to change. So let's say 0.9 seconds. And they finished changing out here about 1.5 seconds. I assume you only did this once, right? Did the collision once the second time. And then you just moved them after that, right?
Yeah.
Yeah.
Push them over the side.
So my collision here, I want to zoom in so I just see from about 3 data points before to about 3 data points after. So I'm going to just over like this. So there's 3 data points before. Adjust my time scale. There's about 3 data points after. Need to adjust my vertical just a little. And so that's scaled so I see from before to after. But I don't see a long time before to a long time after. Now we have to answer, was total momentum conserved? Which line is the total momentum? You can look at this thing here to determine which one it is. What color is momentum T? Blue. Okay, so that means I'm looking at the blue one, and the blue one here started right there, went through some fluctuations, and ended right here. Look at the slope it had here, and then just say, if it would have continued on that slope, it would have ended up down here. It ended up with a bigger negative momentum that it started with. So I'd say momentum was not conserved if this was correct data. This wasn't correct data because we had the wrong mass in here. But that's how you're making your compare or your consideration. And obviously the fact that it's not level screws things up even more. So you're looking for the continuity. If you would continue this line, would it match up? And kinetic energy, okay, there's our kinetic energy line. Our total kinetic energy is the magenta one. And the kinetic energy, if I follow this, it actually, the yellow one just stays on a perfectly straight line. The kinetic energy dropped a little bit. You might say, well, that was pretty much close to following it straight along. You might say the kinetic energy was conserved here. Sometimes it's a little iffy, but that's how you're looking at the data. Now, there's one technicality that we also need to discuss, and that is, we had 2 masses here. One was 500 grams, one was 1,000. How do we set the masses? And to do that, you go to data summary, isn't it? No, calculator. Go to calculator. Under calculator, the first thing, mass 1 equals, and it says 1 kilogram. Well, mass 1, right now, mass 1 is this one. That is 1 kilogram. So I'm going to leave that there. Mass 2, the other one, is half a kilogram. So I'm just going to change that 1 to 0.5. Now, when I did that, the graph shifted to correspond with having the different masses. So when you change the masses, you need to come here and note that they start with 1 kilogram. You're going to start your experiments with half a kilogram on each. So you'll need to start your experiment by coming here and setting each one of these to half a kilogram. So I hit return for it to be entered, and then just close the calculator and do your work. Now, these are wrong masses again, so we can't do any analysis because, once again, I want you guys to think it through. So do you understand how to change the mass? Okay. Understand the experiments you're doing? Maybe. Okay, one last thing before I leave you to go, and that will be looking at the definition of the 6 trials. Equal mass, cart 2 initially at rest. So that would be, they both are half a kilogram. This cart's initially at rest. These are set for them to bounce off each other, but the first set is for them to stick, so I got to turn that around. Now, turn the wrong one around. So it's going to be this one stationary, and this one comes, and they stick together. If they bounce apart, you failed, right? It's got to stick together. So that's the first trial. The second trial is equal mass, carts approaching. Oh, yeah. I didn't read right. The one I chose was unequal mass. The second one is equal mass with the carts approaching each other, so that's like this. The third one is equal mass, cart 1 catching up to cart 2. That one's probably the hardest to simulate because you have to start them both. That one's going slowly, this one's going faster to catch up and hit. So that's 3. Then 4 is repeating those, except for you put the bar in one of them, and make sure that you change the mass in the correct cart, so that you have the mass. Yeah, and Alex can work with you on that. If you're not sure which cart is which, just do this. Put one cart here. Because I'm so off balance, I gotta do that. Start it and then just wiggle this one around, and then just look at your data. Was that cart 1 that was moving or cart 2 that was moving? If it's cart 1, that side's cart 1. If it's cart 2, so you can tell really quickly which one's cart 1 and which one's cart 2.